LLMs don't hallucinate randomly. They do it because you set the hyperparameters wrong. Today, we are pulling back the curtain on LLM hyperparameters, the hidden dials that control how models think, choose words, and generate answers. By the end of this video, you will know exactly how each hyperparameter works, why it exists, and how to tune it like a pro. Now, have you ever wondered why does the same AI sometimes give you a boring answer and other times write poetry like it had 3 cups of coffee? The secret isn't the model, it's how the model chooses its next word. When an LLM generates text, it does not write whole sentences at once. It picks one token at a time, one word, one piece over and over again. And the strategy it uses to pick that next token is called decoding. Let's start with greedy decoding. Greedy decoding is exactly what it sounds like. At every step, the model looks at all possible next tokens and picks the most likely one. No randomness, no creativity, just what's the highest probability word? Cool, I will take that. And because of that, greedy decoding is deterministic. That means same prompt, same model, same output every single time. This makes greedy decoding great for precision like answering factual questions or filling in known information. But there's a downside. Because it always picks the safest option, greedy decoding can get repetitive, boring, or stuck in very common phrases. It plays it too safe. Now let's talk about sampling. It's called multinomial decoding. Instead of always picking the top token, sampling says, here's the probability distribution, let's roll a dice. The model still respects probabilities. More likely words get picked more often, but there's a randomness involved. And that randomness is what creates variety, creativity, and different outputs every time. Same prompt, different answers, that's sampling. In libraries like Hugging Face transformers, the entire behavior is controlled by one simple switch. Do sample equals to false, meaning greedy decoding. Do sample equals to true is sampling is turned on. If you use number of beams equals to 1 and do sample equals to false, you are doing pure greedy decoding. But the moment you flip do sample equals to true, the output becomes stochastic, meaning random and diverse. And once sampling is on, that's when parameters like temperature, top K, and top P start to matter. So, when should you use which? If you're doing something low complexity like completing a known fact, structured answers, and precise outputs, greedy decoding works great. But if you're doing story generation, brainstorming ideas, and creativity writing, open ended responses, sampling is almost always better. And now comes the real fun part. Once sampling is enabled, how random is too random? That's where temperature, top P, top K come in, and those are the knobs that actually make or break your LLM outputs. Let's break those down next. When an LLM generates text, it does not know the answer. It has a list of possible next tokens, each with probability. Temperature controls how seriously the model takes those probabilities. Behind the scenes, the model assigns a score called logits to every possible next token. Temperature scales those scores before the final choice is made. Here's the intuition: if temperature is equals to 1, use the probability as is. Lower than 1s, it means sharpen the distribution, and higher than 1, flatten the distribution. In plain English, let's drop the temperature. At low temperature, the model strongly prefers the top ranked token. The highest probability word dominates. At temperature 0, the model basically says, no creativity, I am picking the most likely word, period. That's almost the same as greedy decoding. This is perfect when you want precise answers, technical explanation, factual correctness, and predictable outputs. Now let's turn the temperature up. At higher temperature, the probability gap between tokens shrink. Suddenly, less likely words start getting picked. The result: more diversity, more creativity, more surprises. But there's a trade off. At very high values like 2 or 5, the model can completely lose coherence. Grammar breaks, logic disappears. Welcome to AI gibberish. This setting is great for brainstorming, story writing, exploring weird ideas, but terrible for accuracy, reliability, anything mission critical. So, what number should you actually use? Here's a practical cheat sheet: 0 to 0.2, ultra deterministic and safest answers; 0.2 to 0.5, focused, technical, and factual responses; 0.7 to 1, balanced creativity, most common range; above 1, experimental, wild, creative exploration. If you don't know what to pick, 0.7 is usually a safe default. Next, top case sampling. When an LLM generates text, it looks at its entire vocabulary, sometimes tens of thousands of tokens for the next word. But most of those options are terrible. Top case sampling is how we cut the noise. Here's what happens step by step. First, the model assigns probabilities to every possible next token. Then top K steps in and says, keep only the K most likely tokens. All other tokens deleted, zero probability, gone. The model then renormalizes the remaining probabilities and samples from that smaller, safer list. Now the value of K changes everything. If K is small, like 1, 5, or 10, the model can only choose from a tiny set of high probability words. This makes output focused, predictable, less surprising. And here's a key insight. If k equals to 1, top k simply becomes greeting decoding. One option, no randomness. Now increase k. With k 50 or 100, the model gets access to rare words, unusual phrasing, more creativity choices. This is why many frameworks default to k equals to 50. It's a sweet spot. Enough variety without letting complete nonsense slip in. But push k too high and you invite chaos. Here's a quick rule of thumb. K is equals to 1, fully greedy, zero creativity. K is between 5 and 10, very safe, high probability outputs. K is 20 to 40, controlled diversity. Is equals to 50 plus, creative, exploratory generation. Lower K is great when you want quality and safety. Higher K is better when you want ideas and variety. You just learned about top K sampling where we fix the number of allowed next tokens. But here's the problem. Sometimes the model is very confident, sometimes it's not confident at all. And using the same K in both cases does not really make sense. That's exactly why top P, also called nucleus sampling, exists. Instead of choosing a fixed number of tokens, top P chooses a probability threshold. You set a value of p between 0 and 1. Then the model sorts all tokens by probability, starts adding them up, stops as soon as the cumulative probability reaches p. Only that smallest group of tokens is kept. Everything else thrown away. Let's say you set top p is equals to 0.9. That means give me the smallest set of tokens that together cover 90% of the probability mass. Maybe that's just one token if the model is very sure, or 20 tokens if the probabilities are spread out. And that's the magic. Top P adapts automatically. With top K, you always allow the same number of tokens even when it does not make sense. With top P, the model adjusts to the situation. If the distribution is sharp, only a few tokens survive. If it's flat, more tokens are allowed. No arbitrary cutoffs, no unnecessary risk. Now let's talk about what different values of P actually do. P is between 0.5 and 0.8, very small token set, highly deterministic, safer outputs. Balanced P is 0.9 to 0.95, common default in research and production, good balance of creativity and coherence. When P is 1, almost no filtering, maximum creativity, higher hallucination risk, and yes, P is equals to 1 means no nucleus sampling at all. This is why many research papers recommend top P as a safe default. It removes the long tail of extremely unlikely words without killing creativity. Randomness is still there, but coherence is protected. Next, repetition penalty. Ever seen an AI get stuck like this? Yeah, that's exactly what repetition penalty is designed to fix. LLMs generate text one token at a time, and sometimes they get stuck in loops, repeating the same word, repeating the same phrase, and repeating the same idea. This isn't a bug in your prompt, it's a decoding issue. Repetition penalty is a simple rule applied during generation. After the model generates a token, we reduce the score of tokens it has already used. So, next time the model considers those words, they are still allowed but they are less attractive. It's not a hard ban, it's a gentle maybe say something else. Let's talk numbers. Repetition penalty equals to 1, no penalty at all, the model can repeat freely. When repetition penalty is greater than 1, previously used tokens get suppressed. Values like 1.1 to 1.5 are very common. They slightly push the model toward new words without breaking coherence, but crank it too high and the model becomes afraid of repeating anything. That can hurt fluency. Repetition penalty is especially useful when you see infinite loops, the patterns, overly verbose text, same phrase rewritten again and again. It's popular in story generation, long form writing, code generation, chatbots that ramble. Next, frequency and presence penalty. When LLMs generate text, repetition happens at two levels: repeating ideas or topics and repeating the same words. Presence and frequency penalty attack these two problems in very different ways. Let's start with presence penalty. Presence penalty asks a simple question: has this word appeared at least once already? If yes, the model gets penalized every time it tries to use it again. It doesn't matter if the word appeared once or 10 times. Once it's present, it's discouraged. This pushes the model to introduce new topics, avoid circling back to the same concept, keep the conversation moving forward. And that's why OpenAI describes it as increasing the model's likelihood to talk about new topics. High presence penalty is equals to stop bringing that up again. Now let's talk about frequency penalty. This one is more precise. Instead of asking did this word appear before, it asks how many times has this word appeared. The more times a token is used, the stronger the penalty becomes. This helps prevent things like overusing common words, repeating character names, spamming connectors like this, the, and so. It encourages a richer vocabulary, more varied phrasing, and better flow. Think of it as you already used this word 3 times, maybe pick another. Both penalties usually range from -2 to 2. Positive values discourage repetition, negative values encourage repetition. Common practical values look like this: 0.5 to 1, which stops the model from repeating the same idea. Frequency penalty of 0.5 improves word diversity. For technical or factual content, you often leave both at 0 because repeating key terms is actually important. Now let's talk about max tokens and max length. When an LLM generates text, it does not know when to stop. It will happily keep going forever unless you tell it otherwise. And that's exactly what max tokens or max length does. Max token is a hard limit. It sets the maximum number of new tokens a model is allowed to generate after your prompt. When that number is reached, generation stops instantly. No creativity change, no randomness change, just stop typing. Here's a mistake a lot of people make. In Hugging Face, max length includes prompt plus output. Max new tokens includes only the output. So if your prompt is long, max length might cut off your answer way earlier than you expect. That's why most people recommend using max new tokens. It's clearer and safer. Set it too low and your answer gets chopped off mid thought. Set it too high and the model might ramble, repeat itself, cost you more API money. Max token does not control quality, it controls how long the model is allowed to speak. Here's how people usually set it. Short answers Q&A 50 to 100 tokens, explanation or summaries 200 to 300 tokens, stories or long outputs 500 plus tokens. And if you need a minimum length, some frameworks also support min length and min new tokens. Now let's talk about beam search. So far, we have seen two extremes. Greedy decoding follows one path and never looks back. Sampling rolls the dice and embraces randomness. But beam search asks a different question. What if I explore several good options and only commit at the end? Beam search keeps track of multiple partial sentences at once. They are called beams. The number of beams is controlled by one parameter, number of beams, also called as beam width. Here's how beam search works step by step. Start with a prompt, generate all possible next tokens, keep the top k best sequences where k is goes to number of beams, extend each of those sequences again, score them, prune back to the top k, repeat until the sentence ends. The model is constantly saying, out of all possible futures, which k paths look the most promising. Now the values of number of beams change everything. When is equals to 1, beam search is off. This is just greedy decoding. When beams is equals to 2 and 4, it is fast, light, and exploration. Might miss the best global sequence. When beam size is between 5 and 10, it is much stronger search, more polished, it has coherent output, it is slower and more expensive. More beams equals to more thinking, but also more computation. Beam search usually produces grammatically clean sentences, logically consistent structure, high probability phrasing. That's why it's popular for machine translation, summarization, and formal text generation. Anyway, you care about the best overall sentence, not randomness. But beam search has a weakness. It loves safe answers. With many beams, models tend to sound generic, repeat phrases, and choose common wording. More beams does not always mean more interesting, and yes, it's also slower. Think of beam search like chess. Greedy decoding plays one move ahead, sampling plays random moves. Beam search plays 5 games in parallel and chooses the best one at the end. Use beam search when you want most likely sentence, or structure matters more than creativity, or you're doing translation or summarization. Avoid it for when you're doing brainstorming, creative writing, open ended chat. For those, sampling wins. Next, early stopping. When you use beam search, the model explores multiple sentence paths at the same time. Eventually, those parts reach an end of sequence, basically a complete sentence. So, the big question is, when should the model stop searching? Early stopping is a rule that tells the model when to quit. In most libraries, especially Hugging Face, early stopping when true means as soon as all beams have finished a complete sentence, stop. No extra thinking, no extra token, just return the answers. If early stopping is false, the model might keep generating even after some beams are already complete. Why? Because it's still searching, can I find an even better scoring sentence? That's closer to exhaustive beam search, more thorough but also slower. If you're using greedy decoding or sampling without beams, early stopping does nothing. This parameter only matters when number of beams is greater than 1. In real world use, early stopping is equals to true is almost always the right choice. Why? Because it is faster generation, lower compute cost, no unnecessary overthinking. You already have a complete answer, there's no reason to keep going. You would only turn it off or set it to never if you're doing research, you want fully exhaustive search, or you are analyzing incomplete sequences. For normal labs, don't bother. Next, length penalty. When using beam search, the model scores entire sentences, and here's the catch. Shorter sentences are easier to score highly. Fewer tokens, fewer chances to mess up. So beam search naturally prefers short answers. A one word answer can sometimes score better than a complete sentence. Not because it's better, but because it's shorter. And that's where the length penalty comes in. Length penalty adjusts how beam search scores sentences. It applies a correction based on how long the sequence is. In simpler terms, longer sentences get a boost, shorter sentences get less of an advantage. The parameter controlling this is usually called length penalty. And here's how different values behave. When length penalty is equals to 1, no adjustment. When length penalty is greater than 1, encourages longer, more complete answers. When length penalty is less than 1, encourage short and concise outputs. For example, 1.2 pushes the model to finish its thoughts, 0.8 tells it to wrap things up quickly. You usually tweak length penalty when you see beams ending too early, or incomplete answers, or one liners where paragraphs are expected. This is especially useful in machine translation, summarization, and structure generation. Anywhere sentence length actually matters. Next, logic bias. So far, all the hyperparameters we have talked about influence the model's behavior, but logic bias is different. This one lets you directly interfere with the model's decision making. You're not guiding the model anymore, you're rigging the odds. When an LLM chooses its next token, it assigns score called logits to every possible token. Logic bias lets you manually adjust those scores before the model samples. You literally say, increase the chance of this token or kill this token completely. In APIs like OpenAI's, logit bias is a map. Token ID is equals to bias value. The bias ranges from -100 to +100. Positive bias, token becomes more likely. Negative bias, token becomes less likely. And the extremes are wild. If you set a token's bias to -100, that token is basically banned. Its probability drops to near zero. This is commonly used to block profanity, prevent unsafe words, stop specific hallucination. If the model wants to say it, it simply can't. Now the opposite sets a token bias to +100 and the model will almost guarantee it appears. Want the output to mention a product name, a keyword, a specific term, you can force it, but be careful. You don't always need extremes. Smaller values like +1 or -1 gently nudge the model. That's usually the sweet spot. Hard bends and forced tokens can break fluency, create awkward sentences, distort the model's natural behavior. So now you know the truth. Large language models are not predictable black boxes. They don't hallucinate randomly. They respond exactly to the controls you give them. They are not just hyperparameters, they are levers of control. And once you understand them, you stop fighting the model, you stop blaming the prompt, and you start engineering behavior. This is the difference between using an LLM and controlling an LLM, between hoping for a good answer and designing one. If this video helped you finally understand what those numbers mean, hit the like button. It tells YouTube this wasn't just another AI hype video. Subscribe if you want deep, practical explanation, not surface level tutorials. And comment below which hyperparameter confused you the most before today.